Herzlich willkommen. Einen wunderschönen guten Morgen wünsche ich euch allen. Willkommen zum Tag Nummer 2 dieser JAX 24. Please give a very warm hand to Java Language Architect Brian Goetz.
Thank you very much, Sebastian. So it's nice to be back here at JAX. This is, I think, the fifth time I have presented at JAX. It's always nice to come back here. It's probably been about 5 years since I stood on this stage, and probably 16 years or so since the first time I came here, and probably about as many versions of Java since then as well. So the current version of Java is 22, fresh off the press, and now that we're sort of shipping a new version of Java every 6 months, maybe it doesn't feel like such a big deal that there's a new version of Java anymore. And when I started writing these slides, you saw I started with 21 and like, oh no, it's 22 now, isn't it? So I'm going to talk about features in Java 21 and 22, and some of the ones that we added earlier. But before I get to that, I want to also talk about how we develop those features and what has made it possible to deliver these features and deliver them faster. Because I think that's the big story of the last few years, is not just Java is vibrant, we're delivering great features, but we've been delivering them faster and faster. So before I get into it, let's do a quick poll. How many people here are developing on Java 8? 11? 17? 21? 22? Later than 22? Okay. All right, so good mix. A lot of people are, getting on the newer versions. Some people are still stuck on 8, probably would like to be getting on the new versions. So come join us when you can. So, let's talk about first, briefly, some old news. So last time I was here, we were just getting started with the 6-month cadence, release cadence for Java. And so it's a good time to talk about how has this worked out, right? So in the old days, we had this feature-boxed release model, fairly coarse-grained, where we would imagine a big ambitious feature we wanted to do, like lambdas. We would take a wild, optimistic guess about how long that was going to take to do, which was always wrong. And so we'd think it was going to be 2 to 3 years, and it ended up being 3 to 4 years, and that means delays and unpredictability, which nobody liked. And because the releases were so big and so infrequent, we had to develop a fairly heavyweight release management process for managing the releases, because it was such a big deal if a feature had to be removed at the last minute. And that meant that we were spending a lot of time doing feature release planning meetings and status updates and all of that, rather than developing features. And this release model caused a lot of distortions in the way we work. Like, one of the things that frequently happened was, let's say you're working on a feature, you've been working on it for 3 years, it's almost ready, but it's not really ready. But you really want it to be almost ready, and you kind of like close your eyes and convince yourself it's almost ready, because nobody wants to wait another 3 years for it, right? So there was this tremendous temptation to try to sneak things in under the wire, and the result of that was the stability of the initial releases was often not as good as people wanted them to be, and therefore the ecosystem often said, well, I'm not going to use the new version immediately. I'm going to wait a year to see how things shake out, right? These were all negative consequences of our release management process, and it wasn't really working for anyone. The developers were frustrated because it took forever to get new features. Enterprises were frustrated because backporting meant that the old release trains were not as stable as we'd like them to be. And so it was a sort of lose-lose. And so, we knew we had to make a change. We took a hard look at the situation, and we said, okay, what do our customers really need? And in an ecosystem as large as Java, it never speaks with one voice. It often speaks with 10 million voices. But in this case, it actually spoke fairly clearly in 2 voices, which were developers, those who are looking after programs under development, and what we call enterprises, or those who are looking after programs already in deployment that just want stability. So developers want access to the latest features, faster, 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 more features, more predictable. Enterprises want stability. No new features, please. I hate features, but oh yes, I'll take those security fixes and maybe some critical bug fixes. So the old model that we had was basically making no one happy. And so, as is often the case, if if you're looking at a customer base where there are sort of two primary profiles, the ideal solution often has two things in it, and so our new release model is really a two-part release model, which we're calling it tip and tail. So, you all know this. We have a 6-month time-boxed release cadence. The train leaves on time every time. It's always left on time. If a feature doesn't make the train, it doesn't make the train. No big deal. There's another train coming in 6 months. So people are constantly asking me, is this going to be in 23? Is this going to be in 24? And I give the same annoying answer every time as, I don't know. If it's ready, it will be. Right? Very annoying answer. I know it's annoying. But this is working really well for us because the train leaves with the features that it has at the appropriate time. And then on the other end, the tail end, we offer long-term commercial support on selected release trains, and those get security updates and critical bug fixes only. So those are optimized absolutely for stability so that once an application goes into production, you can just keep things the same. So people were very skeptical. Everyone was skeptical of this. Even I was skeptical of this. Within the organization, people said, oh, this is crazy. We can't do this. We can't run a release every 6 months. We're going to get eaten by process overhead. Or what if we don't have anything new to ship? That'll be so embarrassing. We'll look like idiots. These turned out not to be real issues. They turned out to be fears, because change is scary. We're all a little bit afraid of change. The ecosystem was equally skeptical, maybe more vocal about it. There were some very colorful blog posts telling us what idiots we were, how this would never ever work, and nobody wants a new release every 6 months, and we're going to get overwhelmed. And by the way, we don't even need any new features at all. Java 8 is all that everyone's ever going to need. And all of these were basically code for, boy, change is scary, isn't it? And so, change is scary, and change begets change. So we changed our methodology, we changed our release management strategy, but in order to make this successful, we really had to change our mindset. Because under the old system, we had been doing it a certain way for a long time, and we got used to that, and we developed a certain muscle memory of this is how we do it, and we had to learn to unlearn some of those things. The biggest thing that we had to unlearn was learning not to panic that something's going to miss the train. It used to be that if the next train coming is 3 years from now, you really don't want to miss the train. You're going to run down those icy stairs and probably fall on your face. But if the next train is coming soon enough, it's okay. It'll get on the next train. And learning to sort of be calm about that was not so easy for us. Similarly, we had to learn that we didn't need to backport everything. That we only need to backport the most critical release, the most critical patches. And we had gotten the habit of backporting a lot of things because, well, when it's 3 years to the next train, no one wants to wait 3 years for a performance fix or something like that. But there were some sort of surprise big benefits that came with this, and that's what I want to focus on. One of the things that we've done is we've learned how to take these enormous features like generics or lambdas and break them down into a cooperating set of 6 smaller features. So we're never going to do a big bang release with a giant feature driver, like generics or lambdas. Again, we're going to break it down. We're going to do big things. We're going to do interesting things, but we're not going to do them all at once, not developed all at once, not dropped on the customer all at once, although to some degree designed all at once still. And the other big payoff, and this was again a bit of a surprise, was the degree to which this turned into better productivity for us. Because if you didn't need such a, if the risk of missing a release was not so great, you didn't need such a heavyweight release management process. That meant developers are spending less time in release meetings. They're doing fewer backports, which means they're working more of their time developing features, which means the platform is moving forward faster. And that's the real payoff here. This worked out, quite honestly, better than we could have hoped. We have completely slashed our release process to almost zero. It's great. I won't tell you how much time I used to spend in release management meetings, but it was too much. And now it's almost 0, which is just about the right amount. Similarly, the number of backports we have to do is slashed because we don't need them anymore. And that means more stability for long-term releases, more time for developers, and more features faster. So everyone's happy, right? Well, these are people, so let's just say everything's great, okay? Because developers can get access to the latest features faster, enterprises can get access to stable, commercially supported releases with security fixes and critical bug fixes. JDK developers get to spend most of their day working on features and not meetings, and everyone gets more predictability. And so this new release model is really the enabler for all the cool stuff that I know you actually came here to hear about. And the other sort of surprise hidden benefit is our pipeline for the future is better than it has ever been. It's, it used to be at the end of a big release, we were dry. We didn't know what we were doing next. Now, I can see the next 10 years laid out ahead of me. It's really cool. So, here's the map of where we are. You are here is the big red arrow, Java 22. The tail releases are 21, 17, 11, and 8 with varying degrees of commercial support available as, in the orange bars. Okay, so you came here to talk about features, so let's talk about features. So these are the features that are in JDK 22. These are just the features that were big enough to have a JEP. Not everything gets a JEP. Each release probably has 1,000 small improvements, whether they be bug fixes or performance improvements or library improvements or tooling improvements. But the big features get a JEP largely for visibility so we can communicate this is what we're doing. And the JEPs that are in 22 kind of span all over the map. There's some language and tooling. There's some new library stuff, there's some new runtime stuff. And what you won't see when you look at this chart is a sort of coherent release goal, the way we used to have, back in the 8 days or the 5 days, because these are the features that were ready to board the train when the train was leaving. This was not an orchestrated, okay, Java 22 will be all about this theme. Releases don't have themes. But if we sort of zoom back a little bit and add in the things that came in 21, the set gets a little bit bigger and, still pretty well distributed all over the map. And if we keep zooming out, here are the features that were added, the JEPs added since 17 and since 11. Which is starting to look like a pretty big list. We've been pretty busy. And it's a little bit unfair to compare the 11 to 17 with the 17 to 21, because 11 to 17 was 3 years, and then at that point we kind of reevaluated and said, you know what, maybe 2 years is a better cadence for LTS, so we switched to that. And so, the stuff in blue looks like it's more stuff because we had 3 years to work on it rather than 2. So the rate of feature delivery, is still quite good. They're coming in smaller buckets, but there's still a lot of good stuff coming. Now, JEPs are how features get delivered, but it's not how they get built. But features get built in what we call projects in OpenJDK. A project is sort of a place where work happens on a particular topic. They often span 5, 6, or more years. Very often a project will produce multiple JEPs. Sometimes it'll produce 1 JEP. Maybe it'll produce 0 JEPs. It depends on what's going on. But you can sort of think of these as these are the areas that we've decided to make big investments in upgrading the platform. And so each project has a theme. The theme of Loom is lightweight concurrency. And each of these projects has a motivation. And you could usually frame the motivation either as a positive thing, like make this better, or a negative thing, like catch up with the competition. And these are two sides of the same coin. But the way we make decisions about what we're going to invest in is, we look at where are Java developers experiencing pain now? What are the things that are too hard, the things that should be easier, the things that we can do that only can be done in the platform to make life easier for all Java developers? These may be performance features, they may be language features, they may be runtime features. And similarly, there are competitors out there. There's a lot of languages out there, and some of them are better at some things than Java. No surprise, right? And of course, Java can't be better at everything than all the other languages, but we want it to be good at all the things. We'd want people to not have an excuse to not use Java. right? So, we look at the competition, we look at the pain that Java developers are in, and we say, what is the underlying thing here that we need to do in the platform to make that better? So I'm going to talk about a few of these projects. So first one I want to talk about is Project Loom. You've probably all heard of it by now because we've been talking about it for a few years, but it's really here now. We have this habit of like talking about where we're going, and then by the time it's there, everyone's bored of it. But that's how it goes. So this is about Project Loom is about a topic that is very near and dear to my heart, which is concurrency. I think Project Loom is kind of going to be kind of the lambda of JDK 21 in the sense of motivating more people to upgrade. So what Loom does is takes Java concurrency to the next level by not really changing it at all, which is this amazing trick that we managed to pull off. So, Java has always had good support for threads. Java had, cross-platform, concurrency model from day one. We had a cross-platform memory model, and threads give us a really powerful thing. Threads give us sequential code. Sequential code is the kind of code you can read. So you look at you look at a method and it's running in a thread, and you can reason about it almost as if nothing else is running on the machine. And threads give us debugging, threads give us serviceability, profiling, threads give us readable stack traces. And they also map pretty well to how the operating system does the scheduling. So, threads are a useful programming model for letting us reason about what's going to happen next in our code. Unfortunately, threads are increasingly at odds with the hardware. Threads are heavyweight. They're expensive to create. They take up a lot of memory, largely for their thread stacks. And so these are heavyweight entities that are dragging around megabyte scale data structures. And so there's this collision course between there's this natural programming model of give each task its own thread so it gets a sort of isolation versus, boy, I'd like for my program to run efficiently as well. And these things have, when you get to scale, are kind of at odds with each other. So, I'm sure a lot of you have looked at reactive frameworks. Reactive frameworks promise, oh, we'll make the scaling thing work out really well. And they do, but at a cost, at a terrible cost, which is the programming model is awful. It's hard to reason about, it's hard to read, it's impossible to debug, stack traces are unreadable. So, what we realized is that we were putting developers in a position between choosing a good programming model and choosing an efficient runtime model. And we never want to put developers in that choice. We want them to be able to get a good programming model and a good runtime model. So, the solution here, obviously, if threads are too heavyweight, let's just make them lighter, right? Oh, isn't that an obvious solution? But we actually, pulled it off. So what we do is we have a second implementation of threads in the JDK called virtual threads. These are lightweight threads that don't drag around huge stacks. Instead, we store the thread stacks as delimited continuations in the garbage collected heap, which means that the memory cost is pay as you go. And most threads are generally sitting around not doing very much. They're usually waiting for I/O most of the time. And so if you start up a virtual thread and it's only got a few stack frames, it's only going to take a couple hundred bytes. You can scale to millions of those on a machine that's like this machine here. And the really cool thing is, and this we didn't think we were going to be able to pull this off when we started, but it worked out really nicely, is virtual threads are real threads. They're not some other weird thing where you have to say, am I running a thread? Am I running a fiber? No. They're threads. They implement the thread API. You can use all the concurrency APIs like thread local with them. You get clean stack traces. You get clean thread dumps. You get good debugging and profiling. All of your existing code just works. So now, virtual threads don't replace platform threads. Virtual threads use platform threads as their scheduler, so it's not like everything's going to be virtual threads, but most application tasks can be. And so it's important to remember that virtual threads don't make your program faster, they make it more scalable. Now, most programs spend most of their time waiting for I/O, waiting for socket I/O, reading or writing to a socket, reading or writing to a file, waiting for a database query to come back. And the convenient programming model is to give each task its own thread. But if we do that, we're likely to run out of threads as our load increases before we run out of CPU, which means we're not using our hardware efficiently. And so because threads are memory limited, we can't have that many of them. Therefore, we're going to, we may run out of them if we have too many tasks. And that is going to decrease our hardware utilization, which increases our deployment cost. So here's basically the idea. So this graph simulates a sort of typical server application taking requests. We start out, the blue line shows the latency with a thread pool with 200 threads. Everything's going great until we hit 200 requests, and then latency falls apart. So the obvious answer is, well, let's just put more threads in the thread pool. And that's great if we can create that many threads. And that kind of like moves the threshold at which we fall apart out a little bit. But the next line, the light blue line, you see the same characteristic. We hit the limit, and latency falls apart, and we still haven't run out of CPU capacity. The limitation is this artificial limitation of how many threads we can create. And so what virtual threads let you do is push the point at which that curve falls apart out to where you run out of CPU. So somewhere, in the next room, that green line that's like coincident with the x-axis, will eventually saturate because the CPU is saturated. And that's what virtual threads give you. It lets you use the whole CPU. So just like we were talking about how when we changed processes, we had to change our mindset. We've changed our concurrency model a little bit. We have to change our mindset a little bit. We're so used to the tricks that we had to do with threads, we have to unlearn some of those. So it used to be, because threads were expensive, we always pooled them. And we used thread locals to pool objects. And with virtual threads, not only do you not need to do that anymore, you shouldn't do that anymore. Virtual threads are so cheap that the logical thing to do is just have a thread for every user request, every async task. And so you can keep the happy, every activity gets its own thread model and still scale, which is really cool. And it means that you don't need to switch paradigms to something like reactive. Just use better threads. Now, there's a tremendous amount of stuff that goes on under the hood when a virtual thread encounters a blocking operation, what we do is we basically swap the stack out to the heap and run some other task on the same underlying platform thread. And we had to basically rework all the blocking code throughout the JDK, all the I/O code, network code, locking code, everything, so that it could suspend to the heap and reactivate when it was running on a virtual thread. But you don't have to be aware of that. That's just cool stuff going on under the hood. It just works. One of the really cool things that this enables is a new paradigm for concurrency called structured concurrency. If anybody has read Java concurrency in practice, like the worst chapter of this book by far was the chapter on cancellation and shutdown, because it was kind of unsatisfying. There wasn't any real science to it. It was just a bag of tricks of like, well, try this, it might work. But I wasn't really happy with that chapter, because these things are getting applications to shut down or cancel in an orderly manner with fire and forget threads is just too hard. What virtual threads, because the virtual threads are so cheap, it enables us to do something much better, which is, so the principle of structured concurrency is super simple, so simple it makes me wonder why we didn't think of it earlier. Whenever a control flow splits, it should join in the same lexical scope. In other words, parents should wait for their children. Seems like good advice. And if you do that all the way down, then cancellation, timeout, shutdown become trivial things. And so all of those ugly tricks that I recommended in my book, you don't have to use any of them ever again. So I won't go through the code example, but one of the JEPs that Loom brings is an API for structured concurrency. And I encourage you to look at it. It's really cool. So on the topic of runtime changes that just make your program perform better, let's talk about garbage collection. So ZGC is a new garbage collector we added in Java 15. It was specifically aimed at low pause times with very large heaps, so it runs on multi-terabyte heaps with sub-millisecond pause times. And these pause times don't scale with the number of objects in your heap or the size of your heap. And previously I was just talking about scalability, where scaling was a good thing. If your pause times in your GC scale, that's a bad thing, right? So these are pause times that don't scale, which is good. And ZGC has all the buzzwords. It's concurrent and parallel and NUMA aware and region-based and all the cool new things that modern GC algorithms are. But the upshot of it is, if you care about latency, if you care about pause times and predictability, you basically can stop worrying about pauses. So that sounds like magic, right? That's like the one perfect garbage collector. Well, no, there's no such thing as a perfect garbage collector. We have multiple garbage collectors for a reason, because garbage collection is inherently a trade-off. It's a trade-off between latency and throughput and memory utilization and predictability. And so ZGC, picks the let's get the absolute smallest, most predictable pause time we can get. But there are some costs. There's about a 2% throughput hit, which is not that bad if you care about, latency. But it uses more memory as well, and so it's not for everybody. But if you care about latency, you may want to look into it. And so just to sort of compare the pause times, so we took the SpecJBB 2015 benchmark and compared G1 and ZGC. So 99th percentile pause times for GC were about 430, 440 milliseconds, which isn't so bad for G1. And for ZGC, well, we can't see it. So let's magnify the scale out to microseconds, and let's zoom down there. Hi, Duke. And we see the pause time, the 99th percentile pause time for ZGC was something on the order of 140 microseconds. So that's a factor of 1,000. So if you're worried about pauses, I think you probably can stop worrying about pauses. So the big news, so this came out in Java 15. Why am I talking about it now? Well, we've in Java 21 we improved ZGC with generational support. So that list of buzzwords that I gave you about all the things ZGC was missing one buzzword. The buzzword it was missing was generational. So that's what we added in 21, and basically offers the same throughput with a lot less memory usage. So like on the Cassandra benchmark, we found that we could get the same throughput with 75% less memory overhead for the GC. So that's a pretty big deal. We've also been improving the other garbage collectors. If you're still using the parallel collector or G1, those got significant improvements between 8 and 17, and then some smaller improvements again in 21. And so, the real value proposition of Java is you can write your program with whatever version of Java is available now and run it on newer versions, and it just gets faster. It just gets better. Okay, so another thing that we've been working on for quite a while that shipped in 22, finalized in 22, was Project Panama. And Panama is about better access to native code, which is, say, C libraries, and native memory, off-heap memory that's not managed by the Java garbage collector. Now, if you've been programming in Java for a couple of decades, you'll remember the campaign for pure Java. Does anybody remember that? When we were trying to discourage people from using native code, do everything in pure Java. And there's a lot of things you can do in pure Java, but there's also some great libraries out there that aren't written in Java, that are never going to be written in Java, and shouldn't be written in Java. So libraries like CUDA for computing on GPUs, or BLAS for linear algebra, or OpenGL for graphics. These are great libraries. We'd like to be able to access them from Java as if we could, as if we access any ordinary Java library. And we've always been able to do this sort of with JNI, but JNI is horrible. How many people here have programmed with JNI? Okay, so So for all the hands that are up, I'm sorry. For the hands that are not up, I'm glad there are so many of you. But JNI is painful, and it's painful for a reason. You have to write your program split across these two different programming models, that split across Java and C. The tooling is terrible, it's brittle, it's error-prone, the error messages are terrible, and like if you get something wrong, your JVM crashes. So really fun environment to program in. And similarly, our techniques for accessing off-heap memory aren't that much better. We have byte buffer, we have unsafe for accessing the native heap, but they're clumsy, and unsafe is going away. We're not going to take it away until there are safe supported alternatives, but Panama is the safe supported alternative, so it is going away. But Panama was built from the ground up for safety and performance, so it gives you both temporal and spatial bounds checking, so you can't have buffer overruns, you can't have use after free, but it's all written so that it routinely optimizes the way it gets hoisted out, and you don't actually pay for it. So what Panama does is give us a better, more fun to program in, safer, and performant alternative to JNI, byte buffer, and unsafe. Panama is built on investments we've been making for the last decade or more with method handles and var handles, which expose optimizable bits of computation that the VM knows how to optimize really effectively. For what a lot of people use unsafe for, which is memory access, there is now a safe supported alternative for on-heap and off-heap memory access. One of the things we hope will happen with Panama is that native libraries will routinely come with Java bindings, whether those are written by the library maintainer or by some third party, so that if you want to use TensorFlow from Java, somebody who cares about Java APIs, but might not be a TensorFlow developer, can build a Java API that wraps around the TensorFlow library so you can just use it. And we hope that that's something that will become normalized as it gets easier. Okay, so let me switch topics a little bit. I want to talk about something that's that I've been working on more directly, which are language features. So here is a list of the JEPs that have been delivered from Project Amber since I was here last. It's a pretty impressive list. And Project Amber is a little bit of an unusual project in that it doesn't have a specific meta deliverable that it's aiming for. It's sort of the place where we do the sort of small productivity-oriented features. And so it spins off, feature after feature that may look like kind of a random grab bag, and sometimes they are a bit of a random grab bag, but if you look closely, a number of the features are actually pretty significantly related. So all the features that are highlighted in blue here they sort of have a common theme, and a lot of them were developed together, and then broken up and delivered as standalone pieces. Now, I don't have time to go through all of them, or really any of them, but I do want to show you one code example that kind of ties it all together. Now, what these features are innate of is what we call data-oriented programming. Java is an object-oriented language, and historically we have modeled data as objects, which is kind of painful and has a lot of overhead. These features are all about, most of these features are all about better access to data. Records and sealed types give us algebraic data types. Pattern matching gives us ad hoc polymorphism that we can use to visit over algebraic data types without using the visitor pattern. Along the way, we upgraded Switch to work with these features. And the reason we're doing all of this is more of what we do is dealing with data. In the old days, in the monolith days, you built a giant Java application, which might even be a distributed application, but everything was defined by a Java schema. And when different VMs wanted to talk to each other, they serialized Java objects and sent them around. So everything was within the Java type system. But now we're writing smaller programs that are closer to the boundary. They may be talking to other programs that aren't written in Java, maybe through an untyped schema like JSON. And in order to get the benefits of the Java type system, we have to be able to go back and forth between clean Java types and the wire format of whatever we're talking with. So all of these features are about better data, and so I picked an example that sort of tie all these features together. So this is a typical textbook example of modeling an arithmetic expression. An expression here is one of four things. It's either a sum of two expressions, a product of two expressions, a negation of an expression, or a constant. And a sum has two sub-expressions, a product has two sub-expressions, negation has one sub-expression, and a constant has an integer constant. So a sealed interface says that there are exactly four subtypes of expression. It's either this or this or this or the other thing. A record says a sum expression is these two sub-expressions. And if we want to evaluate one of these things, well, we can do it by parts with switch using patterns. So we can have a switch over the expression. Expression is defined in four parts. There's going to be four cases. These are all record patterns. So we say, is it a sub-expression? If so, extract the left and right sub-expressions, evaluate each of them recursively, and then add them together. And so on for the other cases. So, we use sealed types to model choices. We use sums to model. So we use records to model concrete aggregations, and then we use pattern matching to visit over all of this. And one of the ways that I sort of like to sort of benchmark how we're doing on these things is everybody has a favorite way of doing this in their favorite other language. So we will often take these examples and write them in other languages and see what they look like compared to Java. So just for fun, here's the Haskell version of that code. I'm not going to go through it. But the important thing to notice is the Haskell version is only 4 lines shorter. 3 of those lines are empty closing braces. So I think we're doing pretty well on this front. So, okay, so let's switch gears a little bit, and I want to talk about safety, and I want to talk about, of all things, seatbelts. So when I learned to drive in the US, seatbelt use was not required. It was optional, and at some point the regulations came, and most people took this as a kind of helpful nudge to do what was good for them, and then of course some people took this as a sign of governmental overreach and intrusion into their personal freedoms. But 30 years later, you know those people, right? So 30 years later, maybe you are those people. Most people have gotten it. We should wear our seatbelts, and they do wear their seatbelts, and safety on the highway has gotten much better. So when we did modularity in Java 9, we described it as it's a seatbelt, not a jetpack. It's about safety. But unfortunately, the analogy kind of fell a little bit flat because at the time there were no jetpacks. There were only seatbelts. And when you have seatbelts and you're not moving, that doesn't seem very fun. So the seatbelt of Project Jigsaw, which is that the internals can actually be kept internal, isn't there because we want to wag our fingers at people paternalistically. It's there because we want to move faster. So in the early days of Java, most boundaries like access control, private classes and stuff, they were really more like suggestions. And some libraries did some really cool things with the flexibility, but unfortunately, this started to become a real drag on our ability to evolve the platform because we couldn't freely evolve things because even though these were private internals of some JDK class, people had bound to them, and then those libraries would break. And people would say, oh, Java 7 breaks the world, it's terrible. So modularity is what let us leave that in the past. So the rapid pace of innovation that you're seeing now, Loom, Panama, Valhalla, Amber, that's the jetpack. Loom is the jetpack. ZGC is the jetpack. And it would be nice to think you could have jetpacks without seatbelts, but it doesn't really work that way. We couldn't have delivered these features nearly as fast without the seatbelt. What you get for giving up a little bit of freedom is you write your application in Java today, and it just gets faster when you run it on tomorrow's Java. So okay. I talked about upgrading to the new version of Java and things breaking, but that's not supposed to happen, right? Java's supposed to be all about the compatibility. But you probably all have had this experience of you go to upgrade from Java 17 to Java 21 or something like that, and you run into a speed bump because not of anything that you did, but because of dependencies. So your application has its own set of dependencies, and those dependencies often have their own dependencies, and you might not even know about those other dependencies. They're just what Maven brought along for the ride when you built your application. So most libraries have no trouble upgrading to the latest JDK, but a small number of them they can't upgrade because they're dependent on unsupported platform internals that have been taken away. And it only takes one dependency to prevent the entire application from upgrading. And that dependency might be one that you don't even know about. But it just came along for the ride, in that bucket of Maven that you got when you built your application. So while the good news is the Jetpacks keep coming, we do have this challenge of, how do we navigate this this situation with the ecosystem of libraries that may be dependent on features that may be taken away. And this is sort of something we're going to struggle with as a community, which is how do we manage this transition to universal seatbelt use so that we can all benefit from the Jetpacks. And the challenge that applications are seeing and upgrading, like I said, they come from a small fraction of libraries that are using features that may have become restricted or removed in a later JDK version. And we don't remove things gratuitously. We really don't. I mean, sometimes it's taken us 15 years to remove something because the conditions under which it can be removed, took that long to evolve. But like we talked about Project Panama, where it offers a safe, supported alternative to unsafe, and those unsafe API points will eventually go away. So replacing something with a better something, that's a good thing, but it may be a little bit disruptive to the ecosystem. So, but the problem is not that what the JDK is doing. The problem actually is that the library ecosystem is still using the same release cadence that we were using 6 years ago. And that is becoming increasingly a mismatch to, as the JDK is moving faster. So it's a bit of a call to action to the ecosystem to eliminate this impedance mismatch. And, so I kind of ask the open-ended question, what if the ecosystem aligned to the JDK's tip and tail release model? It actually would be easier for everybody. Developing under the tip and tail model is actually so much easier than the old way. Because when you're working on the tip, you get to use the latest JDK and all the latest JDK features. It's, and you don't have to worry about supporting 17 versions. And maintaining the tail, well, that's really easy. You backport almost nothing. There's almost no work to it. And so, I sort of encourage the ecosystem to think about migrating and aligning, to the way we do it in Java. And I'm sure people will be as skeptical now as we were 6 years ago when we migrated to a new release model as well. But I encourage people to give it a thought because it's worked out so well for us. It's so much less work, and you can move forward so much faster. So I talked about how the feature pipeline is looking really good. I'm kind of out of time to do any kind of deep dive on what's coming next, but there are other features like Project Leiden, which is about startup and warm-up. There's Project Valhalla, which is should be bearing fruit soon, about flatter and denser memory layouts and being able to extend the language to the new numeric types and things like that. So there's an awful lot of really cool stuff going on that I hope to be talking about the next time I come to visit JAX. Thank you very much.
Thank you. Thank you so much, Brian.
Thank you.
So much information at such a high pace. Thank you so much. And of course, there will be a lot of questions, a lot of things to discuss. And there's an opportunity for that, right?
Yes, so I'm doing an Ask Me Anything session this evening at 8 o'clock. You should bring your beer, and we'll be able to do long format Q&A where you can ask questions about not just the how or the what, but the why of how we're moving Java forward.
Yeah, and this is really intended to be kind of an informal round to discuss just openly. So join the Ask Me Anything session with Brian tonight at 8 o'clock. Thank you very much.
Thank you.
Cool. Big applause to Brian.